Hey folks, so welcome back to another lesson, and we're now really digging into our new topic, which is the gas laws. And today we're going to look at the theory for Charles's law. And so one of the things we're going to learn about is how to convert between kelvins and degrees Celsius, and we're going to carry out calculations using Charles's law. So first of all, why does the weather report talk about high and low pressure? Okay, and hopefully by the end of this topic on gas laws, you'll be able to explain to me or know why it is that we talk about high and low pressures and how they relate to the temperature of an area. Now, for the gas laws, there are three things we're going to look at, three properties. Number one is pressure, number two is volume, and number three is temperature, which must always be in units of kelvins. And I'm trying to give you a wee visual aid because you can talk about the pressure in a car tyre, the volume in a balloon, and the temperature of that emoji who's obviously sweating hot. Now, the key thing about this topic is we're going to be looking at the relationships between these quantities. And so there's going to be equations, there's going to be calculations, there's going to be experiments as well. Now, first of all, converting temperatures. Gas laws will only work for temperature measured in kelvins. And as we do these gas laws, I will explain to you why that's the case. So to do this, we do the following. Could you write this down, folks? Which is kelvins to the degrees Celsius, you always subtract 273. Degrees Celsius to kelvins, you always add 273. And let's explore this in a bit more detail. So if you copy this example down, so if we had the temperature was 100 degrees Celsius, we add 273 to make it into kelvins. So the Kelvin would be 373 kelvins. So that means 100 degrees Celsius is the same as 373 kelvins. So that's how you change degrees Celsius to kelvins. Example 2, going the other way, if we had 100 kelvins, what would that be in degrees Celsius? So again, I would like to copy this down. Well, it tells us to get kelvins into degrees Celsius, we subtract 273. So that's the same as minus 173 degrees Celsius. So notice how that depending on the unit, the values are massively different. Now, a few other tips to know about kelvins. Number one is that kelvins can never be negative. And again, we'll explain why that is later on. So a wee way to remember how to convert from degrees Celsius to kelvins is that to get kelvins, we always have to add 273. Because if we subtracted 273 to get kelvins, we could end up with a negative number, and we know that kelvins can never be negative. So my top tip to you is just remember, degrees Celsius to kelvins, you add, because you can never get a negative Kelvin. And then you can work out how to do the opposite. Now, the second thing, which I've kind of talked about before, I think when we did the specific heat capacity, is that 1 Kelvin has the same value as 1 degree Celsius. So this is like saying 1 pence has the same value as 0.01. Even though they're different units, they are still worth the same amount. So in other words, this means a change in 50 kelvins is the same as a change in 50 degrees Celsius. So let's look at that through an example. So example 1, if a temperature drops from 200 kelvins to 300 kelvins, you would work out the change in temperature as being 500 minus 300, which is 200 kelvins. If you did the same in degrees Celsius, so 500 kelvins is 227 degrees Celsius, 300 kelvins is 27 degrees Celsius. I would actually try this conversion yourself. To work out the change in temperature in degrees Celsius, we would do 227 minus 27, and we get the same number, 200. So that tells us that, yes, the units are different, but if it's a change in temperature, it's the same value. It's the same number, 200. If you don't believe me, I would actually write this out and try it yourself again. I would definitely copy this wee bit down there because they are quite useful for later on. Now, Who was this guy who came up with Charles's law? Well, he was actually a Frenchman called Jacques Charles. He was a French mathematician, scientist, and a hot air balloon enthusiast. And you can imagine if you're using a hot air balloon, you'd be interested in gases, the pressure of gases, the temperature of gases, and the volume of gases. So here's Charles's law, which relates volume with temperature. And it's quite simply V1 over T1 is equal to V2 over T2, where V1 is the volume before in centimeters cubed. Notice the unit here. Temperature, as I said, in Kelvin, and the same for the volume after and the temperature after. Now, what this equation or relationship really says is that if you have a gas which has a volume and temperature at some point 1, then at some later point, you can work out its volume and temperature later on. The key thing about Charles's law, however, is that it has to have, number 1, the temperature in kelvins, and number 2, the pressure must remain constant. If the pressure doesn't remain constant, we can't say this at all. Okay, folks, so let's look at how we can use our gas laws in solving some problems here. So first of all, we have a balloon has a volume of 50 centimeters cubed when its temperature is 30 degrees Celsius. The volume was increased to 80 centimeters cubed, and calculate the new temperature if pressure is constant. And that's really important, that last line, because it tells us we can use one of our gas laws. Okay, so as usual, we stick with our KFC technique. So first of all, remember temperature has to be in kelvins. So to convert degrees Celsius to kelvins, we add 273. And then the volume is just in centimeters cubed, so we're okay there. Temperature 2 is the thing that we're looking for, and V2 is 80 centimeters cubed. So we write down our equation, and we plug in our numbers. Now, I know some of you find rearranging these equations difficult, so what I would recommend is calculate what you can and then rearrange it. So what I mean by that is work out what 50 divided by 303 is, and then update your equation. So if we do that, we get this, and hopefully you find it's a wee bit more easy to rearrange, because then all it is swapping these two quantities so that you get T2 by itself. Okay, and if we do that, we should get T2 is 80 over 0.165 is equal to 484.8, and if we round it up, we get 485 kelvins. And that's how we get the answer there. I wouldn't bother changing it back to degrees Celsius, because it's going to ask you for a specific unit. Don't give yourself more work, just keep it in kelvins. A wee thing to note is that I have written a rounded answer here. And just be careful of that, because usually we don't like you to round in the middle of an answer. So if you're not sure, just save that into the memory of your calculator and then use that rather than writing it out and rounding the number. So you shouldn't really round the number there. I think I just took the first 3 numbers of the answer there to show you what it was, but I would just save it on your calculator and use the memory function on your calculator. And remember, we can only use Charles's law when the pressure is constant. So let's look at a second example, just to show you that it doesn't matter what we're calculating from Charles's law, the technique is always the same. So a weather balloon has a volume of 250 centimeters cubed when it's at a temperature of 25 degrees Celsius. It's released into the upper atmosphere where the temperature is recorded as minus 10 degrees Celsius. Calculate the new volume if pressure is constant. So you could be doing this if you were, say, a meteorologist and you wanted to measure the temperature of the upper atmosphere, or you wanted to design a balloon that could go up that high, and you had to know what volume it would be when it was up in those kind of conditions. So as usual, we're doing our KFC technique. So we have our temperature. Again, it's in degrees Celsius, so we have to convert it to kelvins. Volume. Temperature again. Now notice how this was a minus temperature, and we're still adding 273 to it despite the fact that it's a minus temperature, and so we get 263 kelvins. And remember as well, kelvins can never be less than 0, so this is actually perfectly okay. And then volume's the thing that we're missing. So again, we write down our equation, we plug in our numbers, and again, if we're not sure how to rearrange this, although this one is a bit more easy than the other one, we work out what we can and then rearrange what's left. So I would work out this part of the equation again, which gives you 0.838. Now again, I've not rounded it, I've just taken the first three numbers there to show you what it is. And then hopefully from here, you can see you would just rearrange it by swapping these two numbers, well, multiplying this number here by this bottom number at the bottom, which I'll show you in the next slide. So there, V2 is this multiplied by 263, and then we get our answer, and we round it again at the end. And notice I've got the correct units, centimetres cubed. So that's how we use Charles's law. Again, it's nothing new. We're still using our KFC technique. The only thing to be aware of is changing your temperature to kelvins.